Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so I started by putting actually a controversial title so that we can generate discussion. And the first thing I want to start by saying is, what do I mean by we? Which I think is the first question to answer. And what I mean by we here is computer vision. Okay, so robotics, you're safe. I'm not going to say anything bad about you. All right, so David, first I was asking for an application. So here is one that I think is a very nice application for computer vision algorithms. Okay, so I'm interested in autonomous driving, and one of the reasons is because actually I don't drive. Okay, and I live in Chicago, so this is actually fairly bad. All right, so in terms of we will see about that. Okay, so what can be done in autonomous driving? So so you have followed a little bit the literature on the DARPA challenge. So robotics people know how to do very well localization, SLAM type of things, path planning, obstacle avoidance. And what they do typically is that they heavily rely on fairly expensive systems, such as the Velodyne system. Right? Nowadays, it's $200,000 to actually buy one of those. And they also have detailed maps of the environment. And so this is nice, right? They can actually do a fairly good job. We have all heard about the Google car. And what actually inspired a little bit the title of this talk is that I was visiting Google last summer, and they show their car for what they actually use computer vision. And the only thing that they showed that they use computer vision for was given a tiny little patch on the image, can you tell me the light, the color of the traffic light? Right, so I thought that it's a shame for our community to be just providing this for such a nice application such as this. Okay, so now if we want to do autonomous driving using computer vision, so what do we need to solve? So we need to reason about 3D, right? So we should be able to do stereo. We need to reason about motion, right? Optical flow. We need to understand how are we moving. We need to do visual odometry, structure from motion. We also need to detect objects, particularly dynamic objects. We have to do this in 3D, right? We have to interact with, we need to know where we can actually drive. We want to do this over time, right? So 3D tracking is something also that we need to do. And in general, we also need to sort of solve 3D scene understanding, right? We would like to know where is the road, where can I drive, where are the buildings, etc. So it actually is an application that provides us with everything that we want in order to evaluate, what we are currently working on in computer vision, or most of the things that we are currently working on. Okay, so let me tell you a little bit about what we actually did for this project so far. So we created the KITTI dataset, okay, which is KITTI. Okay, this is where it comes from. And in order to collect this dataset, basically we took advantage of our autonomous driving platform. So here is the car. And we mounted it with 2 stereo rigs. One is color, one is grayscale. It's pretty high, relatively high resolution, right? It's 1400 by 500. And we also have a laser scanner, a Velodyne laser scanner, as well as GPS and IMU localization. And this is going to help us actually create ground truth for the benchmarks that we want to develop. And so far, we have collected 6 hours at 10 frames per second. That's actually on the order of 2 terabytes. Okay. So one of the nice things is that everything I'm going to show you today, even the raw data, is going to be available in the next few days. Okay, so let me show you a little bit about our benchmarks. So let me just demonstrate this visually. So here's our autonomous driving platform. And what you're going to see first are going to be the benchmarks for stereo and optical flow. So this is the kind of scenarios that we capture the data from. So you have all sorts of very cluttered scenes, as well as highways and more, residential areas. So here is the stereo and optical flow benchmark. We have 400 images, 200 training, 200 testing. We don't give ground truth for the test. Okay, so this, and it provides enough training data to actually get learning algorithms to do this. So this is the visual odometry, and this is the case of the 3D detection and tracking benchmarks. Okay, so you can see that the level of annotation is actually very, very accurate. And I will tell you a little bit more about how we annotate these things and how we did this. Okay, so but this gives you an idea of what the benchmarks actually comprise. Okay, so I'm going to tell you a little bit about the challenges that we needed to solve in order to do this. So the first big challenge or headache is actually how to get the calibration right. And so in order to do this, actually, my colleagues in the Castro Institute of Technology developed some automatic camera calibration, which actually is very stable. You only need to calibrate it once for the full day. We also developed tools for a calibration of Velodyne to camera to register these two sensors. And here the challenge is actually the Velodyne, right? The laser is actually rotating. So you need to compensate for your ego motion in order to register these two things. So this is the only part of the calibration pipeline that is not fully automatic. It requires a few correspondences. The other thing that we need to do is also calibrate GPS and Velodyne. So we need to register these two types of sensors. So this is actually something that has been done in the robotics literature, so we follow standard procedures for that. And it's fully automatic. Okay, so what was the second headache? It's like, okay, great, now we have everything calibrated. We have this massive amount of data. Now what? So one of the things that I really wanted to do is 3D object detection, right? And in order to do this, we need to label this massive data set. And so we did this with actually a hybrid approach, so where we use undergrads in order to label very carefully the bounding boxes. And so that costs quite a bit of money. And then we also use Mechanical Turk in order to get occlusion labels for every one of these 3D object detections. Okay, and I have to say that the Germans are very precise. It's very impressive. Okay, so here are some statistics of the object data set. So as you see, we have almost 200,000 cars in 3D labeled. We have all sorts of vans, trucks, and we have more than 100,000 pedestrians as well, cyclists, etc. So we have a whole bunch of different things. And you can see also on the right the statistics of actually the occlusion labels. Okay, so we have visible, occluded, and truncated, yes.
Those annotations, are they just in vision space, or do you also have to put the laser data?
So the way we do this is that we created a OpenGL special tool that uses projection in the images as well as the laser data. Okay, and the annotators use all this and trajectories over time in order to get very precise labeling.
Okay, so but you can actually transfer them from the vision?
Yes. Everything you can transfer to everything. Yeah, everything is registered. Yeah. Once you annotate something, you annotate everything. Yeah. Alyosha?
So, from what I understand, usually even though it's registered, the laser, if it's too far away from the camera, it sees different things. So sometimes you have things that are only seen by one and not the other. Do you have problems like that?
So I mean, you have definitely, there's a field of view of the cameras where you don't see, that you see with the Velodyne. But, so we didn't see too much of a problem in terms of,
How close is your laser and your camera together? Like, what's the baseline?
Let's see, so there is, between the cameras, there is 50 centimeters, and the laser is in the middle. Okay, so it's not too bad. Yeah, and we actually trigger everything via hardware, so that is well registered. Okay, so so one more headache was actually that you need to actually get a relatively sexy web page so that people will actually look at you, and how to actually evaluate all the different techniques. And some more things that we need to do is also evaluate the state of the art in all these different benchmarks. And this is something that Andreas and Philip, the two students working on this, did a great job. So you can actually access Kitty. You can download all these things, and I'm hoping that you will actually submit your algorithms as soon as possible. Okay, so let me talk a little bit about the benchmarks, and I don't want to spend too much time because I want to show you also some scene understanding stuff. Okay, so I will just highlight some of the things. Okay, so I don't think after Michael's talk I need to actually convince you that Milbury is not everything, right? That we need to go a little bit beyond this. And okay, so this is just an example to even reconvince you more, where this is percentage of pixels that have error bigger than 1 pixel in Milbury. So you see that it's very, very small. And we took the same type of approach and then we applied it to Kitty. So you can actually see sometimes some catastrophic errors. Here he gets 50% of the pixels have an error bigger than 3 pixels in this case. Okay, so they're, from this, laboratory type of setting to actually the real world, there is a big difference. Okay, so maybe in a sense we are not as ready as we thought. Okay, so just to highlight a little bit the differences, right? So from laboratory we go into taking this from a vehicle. Things are not so rich in texture, right? You can see here some houses that, it's very difficult to actually get a stereo from. There is sensor saturation. We have high resolution images, therefore we have much more disparities that actually makes a problem for some of the GraphCAD based approaches, and the planes are actually pretty slanted here, right? So that also can make your life a bit more difficult. So I know that some of you don't like rankings, but I'm just gonna put them anyways, okay? And so here is an example for the stereo ranking, how it is as of right now. And so the nice thing also is that we force everybody to tell what they are doing and what are the exact parameters that they use for their method, okay, so that everything is reproducible. And this is very important, I think, for making computer vision advance. And so here's an example where, so the leading method, PCVP, which actually something that I really like is that it's a learning-based method, okay, so the fact that we have a training set actually is important. Does fairly well and compared to the others, and let me just highlight some of the when it works and when it doesn't work. Okay. So it does fairly well when you have natural scenes, lots of textures, no objects, and you have a couple of wrong pixels, things like surfaces like poles, and the reason is because this particular technique does joint reasoning over segmentation as well as stereo. Now, when does it have really trouble is that when you have these inner city scenes where you have lots of objects and you have textureless surfaces, you have the huge sensor saturation here, you have reflections like in the caravan on the right? So this is very, very challenging scenarios. Okay, so let me tell you a little bit more about the flow data set, and it's a pity I think that Michael is not here anymore. Maybe he didn't want to hear the competition. So I asked Andreas to actually update the table so that we have, okay, you cannot see anything, but so that we have also the average over all the pixels. And actually the method that Michael was talking about is the second method here. And we have an average 11.7 pixels difference on the flow vectors, right? So this is very, very large. So one of the things that we saw is actually that flow algorithms are really not ready for this kind of scenarios. And here we split the tables into two because the lower part actually uses visual odometry in order to come up with the epipolar lines. Okay. All right. So we took the best results done by Bishop Group, and here you see that it works very well when you have a small flow vectors, right? Not surprisingly. And when you have city scenes with the slow motion, something like intersections, right? When you're not driving too fast. Now the difficulties are in with difficult lighting conditions. Again, when you're driving on a highway, you have large flow vectors up to 150 pixels, and so the current methods cannot cope with this kind of motion. So we also have visual odometry. We have the initial benchmark has 40 kilometers. We are not focusing in log closures, okay, so this is not like a slam-based kind of thing. Okay, so this is just more to evaluate odometry. And here the interesting thing was to come in up with a metric that actually doesn't prefer certain methods over others. So what we did is that we averaged the errors and we separate into translation and rotation errors over paths of different lengths, okay. Because one of the problems here is that you commit a little mistake at the beginning, right? If you just look at the endpoint, it's going to be very far, but that doesn't tell you anything about how good your method is. Okay, so we also did a few experiments with object detection, and now finally the object detection data set is going to be the full 3D object detection is going to be available. So this is just showing that actually in the easy cases when you don't have occlusion, actually. So the UFC TTI detector works very, very well. Okay, so this is the Peter Fessensband, David McAllister, Deva Roman, and Ross Gishik detector. Okay, so this is all I want to show about the benchmark. I also want to, yes?
One short question. How much time did it take for how many people to build a system, record the data,
Yeah, so it's 1 year,
1 year?
2 students.
2 students.
And I have to say, the 2 students, particularly Andreas, they are just amazing. And I mean, this is much more than I hoped for. And I think, I mean, it's just a lot of work. They also have, a lot of expertise in culture. They have the car driving around for a while, right? Yeah. So all that is already built in.
So the recording system already existed to a large portion? Because
not everything. They have less cameras. We have to even, engineer how to, mount it on a rack and whatnot. So, so parts of the stuff was there, parts were not there. But they have been working on this for, 10 years or more.
How did you select which scenes are useful for performance analysis?
Yeah. So this is one of another headache, I guess, that I didn't talk about. And so we try to have diversity. Okay. And for this, we create some descriptor that, reasons about, the flow content or the stereo content. And then what we did was using clustering in order to select automatically, sequences that are actually different. And I mean, it's the best we could come up with. We didn't want to select by hand because then you have a prior, right, which is your own bias. Okay, yes, one more question.
I completely understand the motivation to sort of focus in on just image data and what we can do with vision alone, particularly given that laser range finding in our cars. But as a little light accelerometer sensor information can make all the difference. Have you thought much about having other channels which are very minimal alternative sensors?
Yeah. So that's a very good question. I mean, so we are currently looking into what I'm going to talk about a little bit more now, into how, having a rough prior, a map, you don't know exactly where you are, but more or less, can this help you? And this is where, tip sensors can actually help. Yeah, we haven't really done anything very specific on that direction yet. But very good question. Yeah. Okay, so let me tell you a little bit more about, some of the stuff we have done for scene understanding, since this is the scene understanding track, right, of the workshop. Okay, so, and I'm going to start by telling you a little bit in this scenario, what are things that one might want to look into. Okay, so this is 3D scene understanding for autonomous driving, right? And the idea is that, okay, I'm going to drive around just a little bit. I'm going to have, maybe 10 seconds or less of a video. And I want to infer from that the topology and geometry of the scene. Okay, so here is an intersection. This is a 4-way intersection, and so you can see outlining over there. And I would also like to reason about the actual semantic information about the traffic situation in the scene. Okay, I would like to know, are there cars coming in this intersection? From where to where are they coming, right? In order to maybe, have a decision in my autonomous driving. So the way we tackle these things is by using probabilistic generative models. And we build different models for actually monocular and stereo. And I will tell you a little bit about these two models in a bit. Okay, and what was important was actually to try to model the dependencies between static and dynamic information. Okay, actually, when we have cars moving, this is a very, very important cue that we need to use in order to do this estimation. Okay, so the first thing that you need to do is actually try to define what's the topological model that you wanna obtain. So in this case, we focus on in this case, intersections of 3 different types in terms of topology. So we have 2-arm intersections, 3-arm and 4-arm intersections, which model most of the intersections in cultural. And we also have a geometric model in order to have a precise definition of the layout. So you can think of this as an extension of this cuboid layout in the indoor, so actually the outdoor scenario, right? You're really interested into these roads. So what we have is we have a random variable k, which is the number of intersection arms. We have the center of the intersection. We have the different widths of the roads, as well as our own rotation with respect to the intersection, and the relative orientation of these things. Okay, and then since we have a probabilistic generative model, what we need to do is actually define good priors and define a good likelihood function, right? So for the priors, we use sophisticated priors for these relative orientations. We build non-parametric Bayesian statistics. Basically, there is the process mixture models for this. And we build actually likelihood functions using very simple image information. So in this case, what we used was occupancy grids, which is something that people use in robotics very often. And we're going to always reason in bird's eye perspective, and you see the picture on the right. Okay, So you can see our own car. This is bird's eye perspective, right? So I'm looking at it from the ceiling, and you have the field of view of the car, and then you can see color-coded when I think that things are occupied, they're free, or I have no idea because there is an occlusion, or maybe I don't see it. Okay, and we use a stereo in order to compute these encompassing grids. The other thing that we use is actually flow. We assume that things that are moving are actually cars in this initial model, so it was very, very simple. And you can see there that actually flow gives you a very good indication of where the streets are going to be, right? And what type of intersection. You see here that people are turning, therefore it has to be a line on the left side. Okay, so I'm not going to go into the details of how the model is built or anything. I'm just going to show you some videos. So here's an example, and actually the duration of the video is the only thing that we have in order to do this estimation. So here is a particularly difficult case because we are not moving, so we have less information than if we were moving. And I'm just going to give you a kind of like a photo pop-up type of encoding of what's the situation. So you see here in red actually where the system estimates there is activity, where cars are driving, and you see also the estimation of the intersection. So some of these scenes are actually pretty cluttered, and actually that's a good thing for us. So you see that the videos are very, very short, right? So it's actually a fairly difficult problem, even if we have a stereo. Okay. So the next thing that I wanted to do was to actually try to do this with monocular imagery. And the first lesson that I learned was, well, your previous model was nice with all this non-parametric stuff, but this is just too complicated, right? And in particular, the information that we are interested in is correlated in the direction of depth, so it's particularly difficult in this case. So we simplify our model. Now we have a set of fixed topologies. And the other thing that we did was actually to share parameters in the intersection. So for example, we only have a single width for all the streets, and we assume that the roads are collinear. Okay. So there is only a single degree of freedom encoding the angle of one street with respect to the other. Okay. Now, I'm not going to go into the details of this, but just to give you an idea, what is the image cues that we use? So we use semantic segmentation. Okay, if you can segment things into building, sky, and road, this is a very good cue. We use vanishing points. You cannot detect them very reliably, but when you can detect them, this is very important. And we use also vehicle tracklets. So we use a 2D detector, we link trajectories, and then we hypothesize things in 3D. Okay. And the other interesting thing of the model is that since we are now going to have a vehicle detector, a car detection, then we need to also reason about where these cars are really actually in 3D. So now the model is not only doing estimation of the layout, but it's doing joint inference over also the position of every one of our tracklets in 3D. And we need to reason about whether these cars are actually parked or these cars are in the road. And this is very important to get the width accurate. Okay, and without really telling you much, I'm just going to show you the video, and you will see the kind of thing that we can do. So this is from monocular imagery, okay, and the video again is the only thing that our system has. So you see here on the right, it's again bird's eye perspective, okay, so it's full 3D. And you see an estimation of our own motion as well as the motion of the vehicles in the street, as well as the layout. So sometimes, things are not, super good. Like in this case, right, we got that car that was a little bit too far up. And the reason is that, if you get a couple of pixels wrong there, the segmentation, right, this is in 3D, it's actually very far. But you can actually get a fairly nice estimation of the traffic here, right? So you can think of, reasoning about, what should I do if I see this traffic, right? The first thing that you notice is that, okay, I can probably turn left, but I should stop if I'm going to continue straight.
Raquel?
Yes.
Sorry, I missed the type of intersection. Is that an input, or does it get inferred?
Yeah. So we use boosting to infer that, and boosting to infer that as a classifier. Okay. And then the joint inference is conditioned on that. Okay.
So you do it first, or is it?
So we do it first. Yeah. This is something that we should hopefully change soon. Okay, so you see there one of the cars parked, etc. Okay, cool. And all right, so in this case, this is just comparisons of how good we do with respect to the if you use a stereo. Obviously, monocular is not going to do as well. But now we have this rich set of features that actually I think are going to be very important to make the stereo work much better. And the interesting thing is actually we are very accurate in estimating the rotation of the relative rotation of the different streets, which I think is one of the important things that you need to estimate. Okay, so now one of the questions I want to actually even ask you is that, so we did Kitty, right? I talked about this benchmark. We benchmark certain computer vision problems, but Kitty has much more. It's very rich. We can do a lot of different things. And let me just show you an example of what we have in mind these days. So in this case, this is OpenStreetMaps, and this is the evolution of the annotations over time. Okay, so you see that it's growing. Actually, again, this is capturing culture. Germans love technology, so they annotate almost everything. And they annotate not only roads, but they also annotate buildings. Okay, so it's relatively coarse annotation. So here, what you have overlay is actually the where the roads are. You have the, I'm not sure if you can see the actual street lines, and you also where they have annotated the buildings. Okay, so it's not super accurate, but we are going to work into using this in order to get accurate annotations of these things. So we can now benchmark with Kitty with a lot of data, actually, the type of layout approaches that I was showing you before. Now we have 4 cameras. We have grayscale. We have color. We have laser range. We have GPS, right? So now you can think of, trying to look into which ones of these sensors is important, how many things I need, is color really important, right, for all these different things. So what some of the things I would like to do, and I'm hoping to do in the next few months, is actually get also semantic segmentation, and this will be transferred directly also to the point clouds. Okay, so there is a lot of interesting things that one can do here, and you can see here the richness. You can do things like traffic analysis, right, outlier detection, etc. Okay, so yeah, so I have 5 minutes, 4 minutes, 3 minutes, whatever, some minutes. Okay, so I'm going to talk about one of my favorite things out here, which has nothing to do with autonomous driving. That goes well with what Rob and Derek were showing before. And then I will just stop after that. Okay, so yeah, one of my favorite problems is this problem that I guess David and Derek and Barsha started to work on a few years ago, which is, okay, you're given a single picture, can you estimate the layout of the room? And so this is actually a structure prediction problem, right, where you're interested into given some features, which are some potentials, which are built from image features, trying to compute the argmax of the layout. Okay, so the question is, how can you define the features and the parameterization such as you can do this problem very efficiently and very accurately? Okay, so there has been multiple parameterization of this problem, and so one of the parameterization that actually I think is very nice is that given the vanishing point, you can parameterize this problem with only 4 degrees of freedom. Okay, and now the second question was how you compute this, the image features for this. So in this case, what we use is following the state-of-the-art orientation maps and geometric context, which basically give you for every pixel what's the probability of the confidence that you have of which one of these walls is represented. Okay. So now the question is, how do you compute the potentials and what are these potentials? So what typically you have to do is, so these features 5 here, what they do is that for a particular hypothesis of the layout, it counts how many pixels on my hypothesized left wall are actually yellow, how many are green, how many are blue, etc. And then you will try to have a scoring function that says, okay, the left wall should just align with the yellow pixels, right? The front wall should align with the green pixels, etc. Now, if you look at the yellow wall, in order to specify this, you need 3 degrees of freedom, right? There is 3 lines that you need to draw in accordance with these vanishing points in order to specify this. If you want to do the front wall, then you need 4 degrees of freedom. So it seems that this is actually a Markov random field with very high order potentials. Okay, so I'm just going to show you one trick that you can do in order to solve this very, very efficiently. So think for a moment of integral images. Okay. So in integral images, you want to compute what's the value inside a rectangle, and the way you do this is by computing differences between things that depend only on two variables, right? Which are that define a particular corner of the box. So you can extend this concept to reason about 3D geometry in a similar manner, right? So I can actually count what is on the left wall or what is on the front wall, but just accessing some integral accumulators which now are in accordance with the vanishing points. And by doing this, what I can actually do is I can obtain the same potentials that people used in the past, but now they are decomposable in pairwise potentials. And they're exactly the same energy function. There is no approximation whatsoever here. There is no latent variables. There is nothing like that. Okay. So what is the nice thing about this is that now you can do efficient inference in this model. And so the fact that you can do the efficient inference is important not only because you're going to be faster, but also because before, since you have very high order potentials, you have to discretize your problem very crudely. Okay, so here are results that are going to appear at this CVPR with our technique. And the interesting thing is that you only need 1 minute to train the model, and you're already beating the state of the art, and you only need 140 milliseconds to do inference over each one of your images on average. Okay, so it's very, very fast. It does very, very well. Now, okay, so one sentence? Sure. Okay, so this is just an answer to one of your questions that you asked me a few months ago. Okay, so I present this stuff in the Illinois Vision workshop that we do up in the Chicago area. And Derek asked me, okay, how good is this solution? And is it possible to do it better? And I just want to answer the question that you posed me there. And so it turns out that you can actually do this even better. And what you can do is, so we have come up with a way to do exact inference in this problem. Okay, so now you're guaranteed to get the optimum over, let's say, 50 to the 4 possibilities. And you can get the exact solution in only 7 milliseconds. Okay, so you can actually do this inference very, very fast. And all right. And anyways, so I just want to conclude before he throws me out. And yeah, so you know, what I would like to ask you, what you would like to have in Kitty? And I mean, a question that we need to ask ourselves is that are we really ready for this? It seems that some of the classical algorithms do not work at all. And I want to say that all this is possible just because of these 2 students, which are really fantastic. And Andreas will be in the market on a year. He is just great. Okay, thank you.